Beneath our feet lies a planet with secrets spanning 4.56 billion years, a world that has witnessed the rise and fall of countless species, massive extinctions, and transformations beyond imagination. Yet in all that vast expanse of time, we assume that only now, in this fleeting moment, has true intelligence emerged. But what if we're wrong? What if the very ground beneath our cities holds the ghostly remains of civilizations that flourished and vanished millions of years before the first human ever walked the earth? The impossible question. Picture this moment in the grand theater of cosmic time. If Earth's entire 4.56 billion year history were compressed into a single year, modern human civilization would occupy less than the final second before midnight on December 31st. We are not even a heartbeat in the planet's memory. Yet in our brief existence, we have fundamentally altered the chemistry of the atmosphere, the composition of the oceans, and the very rocks beneath our feet. This staggering realization leads to one of the most profound questions science has ever dared to ask. If another intelligent species had evolved millions or tens of millions of years before humans appeared, would we be able to detect their presence today? The question sounds like science fiction, yet it has captured the imagination of serious scientists at NASA, Cambridge University, and research institutions around the world. To understand why this question matters, we must first grasp the almost incomprehensible scale of deep time. Homo sapiens has existed for roughly 300,000 years, a cosmic eye blink. Complex human civilization, with its cities and technologies, spans merely 10,000 years. Industrial civilization, the kind that could leave detectable traces in the geological record, has existed for less than 300 years. In the vastness of Earth's history, our entire technological existence represents just 0.000007% of the planet's age. Yet in this infinitesimal slice of time, we have unleashed forces that rival the planet's most dramatic natural events. We have burned through millions of years' worth of stored carbon in mere centuries, triggered a mass extinction event, and scattered radioactive isotopes across every continent and ocean. We have created entirely new categories of materials, plastics, synthetic chemicals, refined metals in concentrations never seen in nature, that will persist in the geological record for millions of years to come. The haunting realization is this: if our civilization vanished tomorrow, what traces would remain after 10 million years? After 50 million? The answer reveals both the remarkable persistence of certain signatures and the terrifying efficiency with which our planet erases the evidence of life itself. Consider the mathematics of preservation. Today, human settlements cover roughly 1% of Earth's land surface. But only a tiny fraction of this surface has any chance of being preserved in the geological record. Most of our cities, roads, and monuments sit on continental surfaces that are actively eroding, subject to the relentless forces of weathering, vegetation, and geological upheaval. The rocks that preserve ancient life represent less than 0.1% of Earth's surface at any given time, typically formed in special environments like lake beds, river deltas, and shallow seas where sediments accumulate rapidly enough to bury and protect whatever lies beneath. The implications are staggering. Even a highly advanced civilization that persisted for hundreds of thousands of years might leave behind evidence so sparse and scattered that we could easily overlook it or mistake it for natural phenomena. Their cities would crumble to dust, their monuments would erode away, their technologies would corrode and decay. Only the most chemically stable signatures, isotopic anomalies, unusual metal concentrations, perhaps fragments of their most durable synthetic materials, might survive the eons. But here lies the deepest mystery of all. Earth's geological record does contain anomalies that have puzzled scientists for decades. Rapid climate changes with no apparent cause, mass extinctions that seem to strike without warning, unusual spikes in atmospheric carbon dioxide, strange metal concentrations in ancient sediments, chemical signatures that don't quite match our models of natural processes. Most of these have conventional explanations: volcanic eruptions, asteroid impacts, natural climate cycles. But what if some don't? The question becomes even more intriguing when we consider the Cambrian explosion 540 million years ago, when complex life forms suddenly appeared in the fossil record with unprecedented diversity and sophistication. Or the mysterious gap in the fossil record known as the Precambrian puzzle, where evidence of early life seems frustratingly elusive. Could some of these gaps and anomalies reflect not just the limitations of preservation, but the presence of intelligence that we haven't yet learned to recognize? Modern astrobiology has embraced this question with surprising seriousness. As we search the cosmos for signs of life beyond Earth, scientists have realized that we need to understand what technological civilizations actually look like in the geological record. How long do their signatures persist? What kinds of traces are most likely to survive? How do we distinguish between natural catastrophes and those potentially caused by intelligence run amok? The search for ancient terrestrial civilizations has become a proving ground for developing techniques that might one day detect technological species on other worlds. If we can't recognize the signs of past intelligence on our own planet, how can we hope to spot them among the stars? Yet perhaps the most unsettling aspect of this inquiry is what it reveals about our own future. Every day, we pump more carbon dioxide into the atmosphere, scatter more synthetic chemicals across the globe, and drive more species to extinction. We are conducting a real-time experiment in planetary transformation, the likes of which Earth may have witnessed before. If previous civilizations faced similar choices and failed, their fate might be written in the rocks beneath our feet, a warning we've yet learned to read. The story that follows is not about confirming the existence of ancient astronauts or lost Atlantean empires. It is about pushing the boundaries of what science can detect, understand, and imagine. It is about the humbling realization that in the vast library of Earth's history, we may have read only the final page of the final chapter, while countless volumes remain hidden in stone, waiting for us to develop the wisdom to decipher their contents. What if we are not the first? What if the very ground we walk upon holds secrets that could fundamentally change our understanding of intelligence, technology, and our place in the universe? The journey to answer these questions will take us from the deepest ocean trenches to the most advanced laboratories on Earth, from ancient geological formations to the cutting edge of space exploration technology. The impossible question demands an answer, and science is finally ready to provide one. The Vanishing Act: How Earth Erases Evidence. But as Schmidt and Frank's rigorous framework spread through the scientific community and researchers began the systematic hunt for ancient technosignatures, they immediately confronted a sobering reality. Earth is perhaps the most efficient destroyer of evidence in the known universe. Our planet operates like a vast recycling machine, constantly grinding, melting, burying, and chemically transforming everything on its surface with a thoroughness that would make any evidence disposal expert envious. To understand why finding traces of ancient civilizations is so monumentally difficult, we must first appreciate the almost supernatural efficiency with which our planet erases its own history. Every grain of sand on every beach, every pebble in every riverbed, every mountain peak piercing the sky, all of it is temporary. Given enough time, Earth will grind it all to powder, melt it in its molten depths, or scatter it to the winds until no trace remains. The numbers are staggering in their implications. Earth's surface rocks average only about 2 billion years in age, despite the planet being 4.56 billion years old. This means that more than half of our planet's history has been literally erased. The rocks that recorded those ancient eons long since ground to dust or melted back into the mantle. If Earth kept perfect records, we should have rocks dating back to its very formation. Instead, fewer than 1% of surface rocks are older than 3.5 billion years, and those survivors exist only because they happen to be in the most geologically stable areas of ancient continents. The destruction begins the moment anything appears on Earth's surface. Rain, that most gentle and life-giving of phenomena, is actually a weak acid that slowly dissolves even the hardest rocks. The carbon dioxide in our atmosphere combines with water to form carbonic acid, which attacks limestone, marble, and even granite with relentless patience. Ancient monuments built by humans just a few thousand years ago show dramatic erosion from this process. The Sphinx in Egypt has lost significant facial features, while Gothic cathedrals in Europe require constant maintenance to prevent their limestone facades from crumbling away. But chemical weathering is just the beginning of the destruction. Physical weathering tears apart the mightiest structures through the simple expansion and contraction of ice. Water seeps into cracks, freezes, and expands with irresistible force, splitting apart boulders the size of buildings. Mountains themselves are carved away by this process, grain by grain, until entire mountain ranges are reduced to sediment in the sea. The living world accelerates this destruction in ways that seem almost malicious. Tree roots, following the smallest cracks in search of water and nutrients, can split apart massive stone blocks with slow but inexorable force. The ancient temple complex of Angkor Wat in Cambodia, abandoned for just a few centuries, has been dramatically transformed by jungle vegetation, with trees growing through and around stone structures, their roots cracking foundations and toppling walls that had stood for nearly 1,000 years. Even more insidious is the work of countless unseen organisms. Bacteria and fungi secrete acids that dissolve metals and stones. Lichens, those peculiar partnerships between algae and fungi, can grow on bare rock and gradually break it down through both chemical and physical processes. In just decades, they can create soil where none existed before, beginning the slow but inevitable process of burying whatever lies beneath. Perhaps most devastating of all is the process called bioturbation, the constant stirring and mixing of soil and sediment by burrowing animals. Earthworms, insects, small mammals, and countless other creatures continuously churn the upper layers of the ground, destroying the careful layering that preserves archaeological evidence. Studies have shown that in many environments, bioturbation can completely mix the top meter of soil within just a few centuries, erasing any hope of finding intact deposits from ancient civilizations. Yet the surface destruction, dramatic as it may be, pales in comparison to the geological processes that operate on planetary scales. Tectonic plates drift across Earth's surface at rates of centimeters per year, imperceptible to human observation, but capable of moving continents thousands of kilometers over millions of years. As these plates collide, they create mountain ranges, crushing and folding whatever lies between them. When they pull apart, they create rift valleys and new ocean basins, stretching and tearing the landscape. Most terrifying of all is the process of subduction, where oceanic plates dive beneath continental plates and disappear into Earth's mantle. The ocean floor, which covers more than 70% of our planet's surface, is constantly being recycled through this process. The oldest oceanic crust on Earth is only about 170 million years old, ancient by human standards, but representing less than 4% of Earth's total age. Everything older has been swallowed by the planet and melted back into liquid rock. This means that any evidence of ancient civilizations that might have been preserved in marine sediments older than 170 million years has been completely destroyed. Entire geological eras have vanished into the mantle, taking with them any secrets they might have contained. It's as if Earth regularly burns its own library, ensuring that only the most recent chapters of its history remain available for reading. But the story becomes even more complex when we consider what actually has a chance of surviving this planetary destruction machine. The key lies in understanding the rare environments where burial and preservation can occur faster than destruction. These geological safe havens are scattered and temporary, but they represent our only hope of finding evidence from deep time. Sedimentary basins offer the best preservation potential. These are areas where rapid burial can occur, typically in environments like river deltas, lake beds, and shallow seas. When sediments accumulate quickly enough, they can bury and protect whatever lies beneath before destructive processes can obliterate it. The most favorable conditions occur in foreland basins created by mountain building, where erosion from rising mountains provides a constant supply of sediment that can accumulate to depths of over 10 kilometers. The finest grained sediments, mud and silt, preserve evidence far better than coarse materials. Clay particles can wrap around and protect delicate structures, creating a protective cocoon that shields them from further damage. Anoxic conditions, where oxygen has been depleted, dramatically slow bacterial decomposition and chemical weathering. Cold environments further enhance preservation, which is why some of our best-preserved ancient remains come from permafrost, ice, and deep ocean sediments. Yet even under the most favorable conditions, preservation is a numbers game with terrible odds. Studies of the fossil record reveal that fewer than one organism in a million ever becomes fossilized, and most of those fossils represent only the hardest parts: shells, bones, and wood. Soft tissues, which make up the majority of any organism, almost never preserve. by extension, the soft components of any ancient civilization. Their books, their clothing, their artworks, their technologies made from organic materials would have virtually no chance of surviving millions of years. The mathematical reality is sobering. If we assume that a hypothetical ancient civilization covered the same percentage of Earth's surface as modern human settlements, about 1%, and that only areas in active sedimentary basins have any chance of preservation, less than 0.1% of Earth's surface at any given time, then the probability of finding direct physical evidence from such a civilization drops to vanishingly small levels. Add in the fact that even preserved sedimentary rocks are constantly being uplifted, exposed, and eroded away, and the chances become almost zero. This is why the Silurian hypothesis focused on chemical rather than physical signatures. While buildings crumble and artifacts corrode, certain chemical traces can persist much longer because they operate on planetary scales. When a civilization alters the composition of the atmosphere or oceans, those changes get recorded in sediments forming all over the world. Even if 99.9% of these records are later destroyed, enough might survive in widely scattered locations to preserve the signal. The most persistent signatures would be those that are both chemically stable and globally distributed. Isotopic signatures in carbon, which get incorporated into all living things and many rocks, can survive for millions of years. Certain metal concentrations, once dispersed through the environment, create anomalies that persist in sedimentary sequences. Synthetic materials that are chemically resistant to breakdown might leave traces that endure far longer than the civilizations that created them. But perhaps the most unsettling aspect of Earth's destruction processes is how they affect our understanding of our own civilization's future legacy. When we look at the abandoned city of Pripyat, evacuated after the Chernobyl disaster, we can see how quickly nature reclaims human settlements. In just 40 years, trees have grown through the windows of apartment buildings, and the concrete structures are already showing significant deterioration. Extrapolate this process over thousands or millions of years, and it becomes clear that very little of our current civilization would survive in recognizable form. The realization is both humbling and terrifying. Earth keeps very few secrets, and those it does preserve are often fragmentary, scattered, and difficult to interpret. If ancient civilizations did exist, their traces would be subtle, easily missed, and quite possibly already destroyed by the planet's relentless recycling processes. The hunt for the Silurians would require not just sophisticated detection methods, but also a profound understanding of how our planet preserves and destroys evidence across the vast scales of geological time. Yet, as we shall see, some signatures prove remarkably persistent, defying Earth's best efforts at destruction and offering tantalizing glimpses into what might lie hidden in the planet's ancient memory. The Silurian hypothesis, when science meets science fiction. The impossible question hung in the air of scientific conferences and research papers for decades, tantalizing and unanswered, until two unlikely collaborators decided to tackle it head-on. In 2018, NASA climate scientist Gavin Schmidt and University of Rochester astrophysicist Adam Frank published a paper that would transform speculation into rigorous scientific methodology. Their work appeared in the prestigious International Journal of Astrobiology with a title that seemed borrowed from science fiction: The Silurian Hypothesis. Would it be possible to detect an industrial civilization in the geological record? The name itself tells a story of scientific audacity. The Silurians, for those unfamiliar with British science fiction, are fictional reptilian beings from the long-running series Doctor Who, an ancient intelligent species that supposedly ruled Earth millions of years before humans evolved. By invoking this reference, Schmidt and Frank were making a deliberate statement. They were taking a question that had long been relegated to the realm of fantasy and dragging it into the harsh light of scientific scrutiny. We are not suggesting that ancient industrial civilizations existed before our own. The authors emphasized in their paper, a disclaimer they repeated multiple times as if to ward off accusations of scientific heresy. We strongly doubt that any previous industrial civilization existed before our own. Yet their very willingness to examine the question formally represented a watershed moment in how science approaches the seemingly impossible. What drove these respected scientists to risk their reputations on such a controversial inquiry? The answer lies in the rapidly evolving field of astrobiology and our growing understanding of what technological civilizations actually look like from a planetary perspective. As we search the cosmos for signs of life beyond Earth, researchers have realized a troubling gap in our knowledge. If we can't recognize the signs of past intelligence on our own planet, how can we hope to detect them among the stars? Schmidt, whose primary expertise lies in climate modeling and understanding how human activities alter Earth's atmospheric chemistry, brought a unique perspective to the problem. He had spent years studying how industrial civilization creates distinctive signatures in ice cores, sediment layers, and atmospheric composition. Frank, meanwhile, had been grappling with the theoretical challenges of detecting technological civilizations around other stars. Together, they realized that Earth itself could serve as a laboratory for testing detection methods. Their approach was revolutionary in its focus. Rather than searching for cities, tools, or other direct artifacts, what archaeologists call the material culture of civilization, they concentrated on what they termed planetary-scale physical-chemical signatures. This represented a fundamental shift in thinking about how advanced civilizations might be detected across deep geological time. The reasoning was both elegant and sobering. Physical structures, no matter how massive or sophisticated, face inevitable destruction over millions of years. Wind, rain, ice, and the slow but relentless movement of tectonic plates grind even the mightiest monuments to dust. The pyramids of Egypt, barely 4,500 years old, already show significant erosion despite being built in one of the world's most preserving environments. Extrapolate that process over millions of years, and even structures the size of mountains would eventually vanish without a trace. But chemical signatures tell a different story. When a civilization burns fossil fuels on a massive scale, it alters the isotopic composition of carbon in the atmosphere, oceans, and eventually in the sedimentary rocks that form from these environments. When it mines and processes metals, it creates distinctive geochemical anomalies that can persist for millions of years. When it manufactures synthetic materials, it introduces entirely new chemical compounds into the planetary system, molecular fingerprints that have no natural origin. The Silurian hypothesis identified several categories of potentially detectable signatures. Carbon isotope excursions emerged as the most promising avenue for investigation. Modern industrial civilization has already created a measurable shift in the isotopic composition of atmospheric carbon dioxide, and the authors calculated that a full-scale industrial civilization could potentially produce isotopic excursions of 3 to 6 parts per thousand signals that would be detectable in the geological record millions of years later. But the true genius of their framework lay in its insistence on multiple concurrent signatures. A single anomaly, no matter how striking, could almost always be explained by natural processes. Volcanic eruptions can release massive amounts of carbon dioxide. Asteroid impacts can trigger global environmental catastrophes. Natural climate cycles can drive species to extinction. The key to distinguishing technological from natural causes lay in finding combinations of signatures that occurred simultaneously, patterns that would be virtually impossible to produce through natural processes alone. Consider their hypothetical example. An ancient civilization that burned through its planet's fossil fuel reserves might leave behind not just carbon isotope excursions, but also distinctive patterns of metal enrichment from mining activities, unusual concentrations of synthetic compounds, rapid climate change signatures in ice core equivalents, and characteristic extinction patterns in the fossil record. The simultaneous occurrence of all these signatures would create a fingerprint of technological activity that would be extremely difficult to explain through natural processes. The temporal constraints of their analysis proved both liberating and humbling. For civilizations that might have existed more than 4 million years ago, the chances of finding direct physical evidence approached zero. Only about 1% of Earth's surface is currently urbanized, and exposed prequaternary surfaces represent orders of magnitude less area. The mathematics of preservation suggested that even a highly advanced and long-lasting civilization might leave behind only the faintest chemical traces. Yet this limitation also revealed the true power of their approach. While archaeologists must rely on the lucky accidents of preservation to find physical artifacts, geochemical signatures operate on planetary scales. When a civilization alters the composition of the atmosphere or oceans, Those changes get recorded in sediments forming all over the world. The signal becomes global, increasing the chances that at least some record of it will survive the geological lottery of preservation and destruction. The response to the Silurian hypothesis within the scientific community was immediate and intense. NASA's astrobiology program quickly incorporated their methodology into broader searches for technosignatures, evidence of technological activity that might be detectable across interstellar distances. The SETI Institute began exploring how similar signatures might be detected in the atmospheres of exoplanets. Climate scientists started examining their data with new eyes, looking for anomalies that might have been overlooked or misinterpreted. But perhaps the most significant impact of their work was philosophical. By providing a rigorous scientific framework for examining the question of ancient civilizations, Schmidt and Frank had legitimized an entire field of inquiry. Graduate students could now pursue research into deep-time technosignatures without risking their careers. Established scientists could explore these questions without being dismissed as fringe theorists. The framework also revealed something profound about the nature of scientific inquiry itself. Throughout history, some of the most important discoveries have come from asking questions that seemed absurd or impossible. The idea that continents could drift across the Earth's surface was once considered laughable. The notion that bacteria could live in boiling water or highly acidic environments defied conventional wisdom. The possibility that massive objects could warp space and time seemed to violate common sense. The Silurian hypothesis reminded the scientific community that the universe is under no obligation to conform to our expectations or assumptions. If intelligence has emerged once on Earth, the basic probability suggests it could have emerged before. If technological civilizations are possible, then they are probably inevitable given sufficient time and opportunity. The question is not whether such civilizations could have existed, but whether we are clever enough to recognize their traces. Modern research building on the Silurian framework has already begun yielding surprising insights. Studies of technosignatures suggest they may be more abundant, long-lived, and detectable than previously assumed. Machine learning algorithms are being developed to scan geological and astronomical data for patterns that might indicate technological activity. Atmospheric analysis techniques originally designed for studying exoplanets are being applied to Earth's own atmospheric history, searching for chemical signatures that might have been overlooked. The implications extend far beyond academic curiosity. As our own civilization grapples with climate change, resource depletion, and environmental degradation, the question of how previous technological species might have faced similar challenges becomes urgently practical. If other civilizations have risen and fallen on Earth, their fate might offer crucial insights into our own future survival. Schmidt and Frank's hypothesis had transformed an impossible question into a testable scientific proposition. They had shown that the search for ancient civilizations was not a matter of wishful thinking or fantasy, but of developing sufficiently sophisticated detection methods and applying them with appropriate rigor. Whether or not such civilizations actually existed, the search itself was advancing our understanding of how intelligence interacts with planetary systems, knowledge that might prove essential for our own long-term survival. The hunt for the Silurians had begun in earnest, and the very planet beneath our feet had become the ultimate archaeological site. Chemical fingerprints that survive millions of years. Yet as researchers delved deeper into Earth's chemical archives, they discovered something remarkable. While our planet may be merciless in grinding down monuments and erasing cities, it is surprisingly faithful in preserving certain types of molecular evidence. Hidden within ancient rocks, locked in sediment cores, and preserved in the very chemistry of the oceans, lie chemical fingerprints that can survive for millions upon millions of years. Signatures so persistent and distinctive that they could theoretically reveal the presence of technological civilizations long after every trace of their physical existence had vanished. The key to understanding these chemical time capsules lies in recognizing that advanced civilizations don't just build things. They fundamentally alter the chemistry of their entire planet. When we burn fossil fuels, mine metals, or manufacture synthetic materials, we create chemical signatures that propagate through Earth's atmosphere, oceans, and ultimately into the rock record itself. Unlike physical artifacts that exist in specific locations, these chemical signals become planetary phenomena, recorded simultaneously in sediments forming all over the world. Consider carbon isotopes, perhaps the most promising avenue for detecting ancient industrial activity. Carbon exists in several forms, or isotopes, with slightly different atomic masses. The most common is carbon-12, but carbon-13 and the radioactive carbon-14 also occur naturally. Different sources of carbon have characteristic isotopic signatures. Fossil fuels, for instance, are severely depleted in carbon-13 because they formed from ancient organic matter that had already been processed by living organisms billions of years ago. When modern civilization burns fossil fuels on a massive scale, we inject this isotopically light carbon into the atmosphere, creating a measurable shift in the global carbon isotope ratio. This signal, known to scientists as the Suess effect, has already decreased atmospheric carbon-13 by approximately 1 part per thousand since the Industrial Revolution began. But a full-scale industrial civilization, burning through its planet's entire accessible fossil fuel reserves, could theoretically create isotopic excursions of 3 to 6 parts per thousand signals that would be clearly detectable in the geological record millions of years later. These carbon isotope signatures prove remarkably persistent because carbon gets incorporated into everything. The shells of marine organisms, the organic matter in sediments, the carbonates that precipitate from seawater. When these materials are buried and lithified into rock, they lock in the isotopic signature of the atmosphere and oceans at the time they formed. Even after millions of years, during which the rocks might be uplifted, folded, and partially metamorphosed, the carbon isotope ratios often remain intact, providing a chemical snapshot of ancient atmospheric conditions. The geological record already contains several dramatic carbon isotope excursions that mark some of Earth's most catastrophic events. The Paleocene thermal maximum, 56 million years ago, shows a carbon isotope shift of about 3 parts per thousand, associated with massive releases of carbon and rapid global warming. The End-Permian extinction, 252 million years ago, displays even more extreme isotopic signatures associated with the most severe mass extinction in Earth's history. If an ancient technological civilization had triggered similar carbon releases through industrial activity, their signature might be preserved alongside these natural events, distinguishable only through the presence of additional technological markers. But carbon isotopes represent just one category of persistent chemical evidence. Even more compelling are the signatures of artificial radionuclides, radioactive isotopes that simply do not occur in nature except under the most extreme circumstances. Modern nuclear technology has scattered these unambiguous markers of technological activity across the entire planet, and some of them will remain detectable for millions of years. Plutonium-244, with its 80.8 million-year half-life, offers the most dramatic example. This isotope occurs naturally only in the hearts of exploding stars, supernovae so violent that they forge heavy elements in nuclear furnaces and scatter them across space. Any significant concentration of plutonium-244 on Earth's surface would represent unequivocal evidence of technological activity, since no natural Earth process can create it in measurable quantities. Even more remarkably, this signature would remain detectable for tens of millions of years, surviving longer than most mountain ranges. Current research in Baltic Sea sediments demonstrates the extraordinary precision with which nuclear signatures preserve in marine environments. Scientists can track the exact history of nuclear weapons testing by analyzing plutonium isotope ratios in sediment cores, with different plutonium isotope combinations serving as fingerprints for specific nuclear tests and reactor accidents. The ratio of plutonium-240 to plutonium-239, for instance, differs between weapons-grade material and reactor waste, allowing researchers to trace contamination back to its precise source decades after the original release. Other artificial radionuclides offer additional technological markers with impressive longevity. Curium-247 persists for 15 million years. Technetium-99 lasts for 211,000 years and has no stable isotopes, meaning any detection would prove artificial origin. Cesium-137, while shorter-lived at 30 years, creates such distinctive signatures in sediment cores that it serves as a global stratigraphic marker for the nuclear age. Metal enrichment patterns provide another category of persistent technological signatures. Modern industrial civilization has fundamentally altered the global cycling of dozens of metals, creating enrichment patterns that far exceed natural background levels. Lead concentrations in Greenland ice cores, for example, show the clear signature of Roman silver mining and smelting 2,000 years ago, proving that even ancient metallurgy can leave detectable traces in the geological record. But modern industrial activity creates metal signatures that dwarf anything from the past. Anthropogenic fluxes of lead, chromium, antimony, rhenium, and platinum group metals now exceed natural sources by factors of 10 to 1,000. Mining operations alone generate extraordinary geochemical anomalies. Gold extraction produces between 100,000 and 1 million times more waste rock than refined metal, creating massive disturbances in the natural distribution of elements that could persist as distinctive signatures in sedimentary sequences for millions of years. Perhaps most intriguingly, modern civilization has created entirely new categories of materials that leave unprecedented signatures in the geological record. Synthetic organic compounds number in the tens of thousands, representing molecular structures that have never existed in Earth's 4.56 billion-year history. Many of these compounds prove remarkably resistant to natural breakdown processes, particularly in anoxic sedimentary environments where bacterial decomposition slows dramatically. Persistent organic pollutants like PCBs and DDT can survive hundreds of years in marine sediments. Synthetic steroids display non-biological chirality patterns, molecular handedness that distinguishes them clearly from natural compounds. Chlorofluorocarbons have no natural sources whatsoever on Earth, making any detection an unambiguous technological marker. Even more exotic synthetic compounds like perfluorinated chemicals can persist for thousands of years in the environment. Recent research into microplastics reveals perhaps the most dramatic example of synthetic material preservation. Sediment cores from the Mediterranean Sea show plastic mass distributions that directly mirror global plastic production from 1965 to 2016, with no detectable degradation over more than 50 years of burial in marine sediments. The anaerobic conditions in deep sedimentary environments dramatically slow microbial breakdown of synthetic polymers, and some plastic degradation products may actually persist longer than the original materials. Most remarkably, industrial processes have created entirely novel rock types that have no natural analogs. Plastiglomerates, hybrid materials formed by the fusion of plastic debris with natural sediments, represent geological formations that could only have been created by technological civilization. These bizarre composite materials combine natural sand, shells, and rock fragments with synthetic polymers, creating formations that would immediately signal technological activity to any future geologist. The global distribution of these synthetic materials is itself remarkable. Microplastics now occur from Arctic ice to deep ocean trenches at depths exceeding 9,000 meters. Synthetic chemical compounds appear in sediments from urban harbors to the most remote ocean basins. Industrial metal signatures show up in ice cores from both polar regions. The planetary scale of these contamination patterns means that evidence would be preserved in widely scattered locations, increasing the probability that some record would survive even if most depositional environments were later destroyed. But perhaps the most sobering insight from studying modern chemical signatures is how quickly they accumulate and how clearly they mark the transition to technological civilization. The isotopic composition of atmospheric carbon has changed more in the past century than in the previous millennium. Nuclear isotope signatures appeared instantaneously in geological terms and now provide precise chronological markers worldwide. Synthetic chemical signatures show exponential increases that mirror the growth of industrial production. These patterns suggest that if ancient technological civilizations had existed, their chemical signatures would likely show similar characteristics: rapid appearance, exponential growth, and eventual stabilization or decline. The challenge for future researchers would lie not in detecting these signatures. Modern analytical techniques can measure isotopic ratios and trace element concentrations with extraordinary precision, but in distinguishing technological from natural causes when multiple explanations might be possible. The realization that chemical fingerprints can survive millions of years while physical artifacts vanish has fundamentally changed how scientists approach the search for ancient civilizations. Rather than looking for cities or tools, they now scan the chemical composition of ancient rocks for anomalies that might indicate technological activity. The planet itself has become a vast archaeological site, with every sediment core and rock sample potentially containing evidence of intelligence that flourished and vanished long before the first human ancestors ever walked upright. Archaeological anomalies. When the timeline breaks. While chemical signatures offer our best hope of detecting truly ancient technological civilizations, the archaeological record from more recent millennia contains discoveries so extraordinary that they force us to reconsider everything we thought we knew about the development of human technology and social organization. These finds don't prove the existence of lost advanced civilizations, but they reveal that our ancestors were capable of achievements that seem to defy the conventional timeline of human progress. Achievements that make us wonder what other surprises might be hidden beneath the earth, waiting to challenge our assumptions about the past. The most dramatic of these discoveries emerged from the rolling hills of southeastern Turkey in the 1990s, where German archaeologist Klaus Schmidt uncovered something that should not have existed. Göbekli Tepe, as the site came to be known, consists of massive stone circles featuring T-shaped limestone pillars, some standing over 5 meters tall and weighing up to 16 tons. Each pillar is intricately carved with lifelike depictions of animals: lions, foxes, wild boar, snakes, and birds of prey, rendered with an artistic sophistication that rivals the best work of later civilizations. But here's what made the discovery so revolutionary. Radiocarbon dating placed the construction of Göbekli Tepe at approximately 9,600 BCE, making it over 11,000 years old. This means the site predates Stonehenge by roughly 6,000 years and the Egyptian pyramids by nearly 7,000 years. More shocking still, it was built before the development of agriculture, before the domestication of animals, before the invention of pottery, and before the establishment of permanent settlements. According to everything archaeologists thought they knew about human social development, hunter-gatherer societies simply did not possess the organizational capacity or technological knowledge to create such monuments. The implications ripple through our understanding of human history like seismic waves. The construction of Göbekli Tepe would have required hundreds of workers laboring in coordinated teams, sophisticated knowledge of stone quarrying and transport, advanced understanding of structural engineering, and the ability to feed and house a large workforce over extended periods. The site's massive pillars had to be quarried from limestone bedrock using only stone tools, shaped with extraordinary precision, transported over considerable distances, and erected with techniques that remain mysterious even today. Even more puzzling, the builders deliberately buried the entire complex around 8,000 BCE, covering it with tons of earth and stone, as if they were determined to hide it from future generations. This act of intentional concealment preserved the site perfectly for millennia, but raises haunting questions about why such an extraordinary achievement was abandoned and deliberately erased from the landscape. Recent analysis using ground-penetrating radar suggests that what has been excavated so far represents only a fraction of the total site. Geomagnetic surveys indicate the presence of at least 20 additional circular structures still buried beneath the soil, potentially making Göbekli Tepe the largest and most complex Stone Age site ever discovered. Each new revelation pushes back the boundaries of what we thought early human societies could achieve. But Göbekli Tepe is not alone in challenging archaeological timelines. In 2024, rigorous scientific analysis of the Dolmen of Menga in Spain revealed engineering sophistication that seems impossible for its age of 3,800 to 3,600 BCE. This Neolithic monument features a massive capstone weighing 150 tons, supported by 32 precisely fitted limestone blocks totaling over 1,140 tons. Modern engineering analysis reveals that the builders understood advanced principles of load distribution, using convex shaping of the capstone to distribute weight efficiently across the supporting structure. The precision of the stonework defies explanation using only the copper and stone tools available to Neolithic peoples. The blocks fit together with tolerances measured in millimeters, achieved without mortar or metal fasteners. The builders demonstrated sophisticated geological knowledge in material selection, choosing limestone with specific structural properties from quarries located many kilometers away. The mathematics required for the complex three-dimensional engineering suggests cognitive capabilities and technical knowledge that historians had assumed were impossible for prehistoric societies. Perhaps no ancient artifact challenges our assumptions more dramatically than the Antikythera mechanism, discovered in a Roman-era shipwreck off the Greek island of Antikythera in 1901. For decades, this corroded bronze object puzzled researchers who couldn't understand what it was supposed to do. Only with the development of advanced X-ray tomography and 3D imaging in the 21st century did its true nature become clear. It was an analog computer of extraordinary sophistication, containing over 30 precisely crafted bronze gears that could calculate the positions of the sun, moon, and planets with remarkable accuracy. The mechanism could predict lunar and solar eclipses decades in advance, track the 4-year cycle of the Olympic Games, and even account for the irregular orbit of the moon using a sophisticated pin-and-slot device that wouldn't be reinvented until the 14th century. The level of mathematical and astronomical knowledge required to create such a device seems completely out of place in the ancient world. Indeed, no similar mechanism appears in the historical record until the development of astronomical clocks in medieval Europe, a gap of over 1,000 years. What makes the Antikythera mechanism so unsettling is not just its sophistication, but its loneliness in the archaeological record. If ancient Greeks could create such complex devices, where are all the others? Why do we have no other examples of similar technology? The mechanism represents either an extraordinary one-off achievement or evidence that ancient technological capabilities were far more advanced than we've ever imagined, and that most of the evidence has been lost to time. Modern engineering research has begun to reveal that many impossible ancient achievements may actually be possible using techniques we've simply forgotten or overlooked. MIT researcher Brandon Clifford's groundbreaking 2018 study demonstrated that massive stone blocks weighing 25 tons or more can be moved by small teams using only leverage, balance points, and rolling techniques. His experiments showed that precisely shaped stones with curved bottom surfaces can be moved with surprisingly little physical effort when proper techniques are employed. This research helps explain how ancient builders could transport and position massive stones without cranes or modern machinery, but it also raises new questions about the level of engineering knowledge required to develop such techniques. The precision shaping required for effective rolling stones, the mathematical understanding needed to calculate proper balance points, and the sophisticated planning required to coordinate large construction projects all suggest levels of technical knowledge that exceed what we traditionally attribute to ancient peoples. Meanwhile, LiDAR technology continues to reveal the true scale and sophistication of ancient civilizations. Laser mapping of the Maya region in Guatemala has uncovered over 60,000 previously unknown structures, revealing a complex civilization with sophisticated urban planning, extensive road networks, elaborate water management systems, and population densities that rival modern cities. What archaeologists once thought were simple agricultural villages turn out to have been components of vast urban networks spanning hundreds of square kilometers. Similar LiDAR surveys in the Amazon basin have revealed massive geometric earthworks, precise geometric patterns carved into the landscape over areas spanning thousands of square kilometers. These geoglyphs, created by pre-Columbian peoples, demonstrate sophisticated mathematical knowledge and the ability to plan and execute engineering projects on a scale that challenges every assumption about prehistoric Amazonian societies. The geometric precision of these earthworks rivals modern surveying, yet they were created using only stone and wooden tools. Perhaps most intriguingly, underwater archaeology continues to reveal sophisticated ancient settlements that were submerged by rising sea levels at the end of the last ice age. Pavlopetri, off the coast of Greece, represents the world's oldest known submerged city, featuring sophisticated urban planning with paved roads, residential districts, and public buildings dating to approximately 2,800 BCE. The preservation of the site's urban layout provides unprecedented insights into Bronze Age city planning and reveals levels of social organization that push back the timeline for complex urban societies. These discoveries share several crucial characteristics that distinguish them from fantasy claims about lost supercivilizations. First, they are all documented through rigorous scientific excavation and analysis, with findings published in peer-reviewed journals and subjected to independent verification. Second, while they push back timelines and reveal unexpected sophistication, they can still be explained within the known bounds of human capability using available materials and technologies. Third, they represent clear extensions of documented human cultural development rather than impossible discontinuities that would require unknown technologies or external intervention. What these archaeological anomalies truly reveal is the danger of underestimating human ingenuity and capability. Our ancestors were not primitive savages struggling to survive in a hostile world, but intelligent, innovative people who developed sophisticated solutions to complex problems using the materials and knowledge available to them. Their achievements remind us that intelligence, creativity, and determination can overcome seemingly impossible obstacles. Yet they also highlight how much we still don't know about our own past. If sites like Göbekli Tepe and the Dolmen of Menga can remain hidden for millennia, what other extraordinary achievements lie buried beneath our feet? If devices like the Antikythera mechanism can vanish from the historical record for over 1,000 years, what other technologies might have been developed and lost without leaving clear traces? The archaeological record is full of gaps, and those gaps represent not just missing data, but missing possibilities. Every new discovery forces us to revise our assumptions about what ancient peoples could achieve, pushing back the boundaries of known human capability and revealing that the story of human technological development is far more complex and surprising than we ever imagined. As we search for evidence of truly ancient civilizations in the chemical signatures of deep time, these more recent archaeological anomalies serve as a crucial reminder. The absence of evidence is not evidence of absence, and human capability has always exceeded our expectations of what should be possible. The ocean's secret archives. As remarkable as these land-based archaeological discoveries are, they represent only a fraction of the story hidden beneath our planet's surface. For while we marvel at the sophisticated achievements buried in hills and desert sands, we must confront a staggering reality. The vast majority of Earth's archaeological potential lies not on land, but beneath the waves, in the dark depths of oceans that cover more than 70% of our planet's surface. Here, in the largest museum on Earth, lie secrets that could fundamentally transform our understanding of human history, and perhaps reveal evidence of civilizations far older than anything we've yet imagined. The numbers alone should humble us. Of the ocean's immense volume, approximately 98% lies beyond the reach of conventional diving, shrouded in darkness that has never known sunlight. We have better maps of the surface of Mars than we do of our own ocean floor. More people have walked on the moon than have descended to the deepest parts of our planet's seas. In this vast, largely unexplored realm, entire continents of evidence could lie waiting, preserved in conditions that would have destroyed similar sites on land millions of years ago. To understand why the oceans represent such extraordinary archaeological potential, we must first grasp the dramatic changes in sea level that have occurred throughout Earth's history. During ice ages, when vast glaciers locked up enormous quantities of water, sea levels dropped by 120 meters or more, nearly 400 feet below current levels. This exposed vast continental shelves, creating dry land where today only fish swim. Coastal plains that could have supported large populations and complex civilizations now lie submerged beneath hundreds of feet of water, their secrets protected by the very element that claimed them. Consider the implications. If an advanced prehistoric civilization had established itself along ancient coastlines, as virtually all human civilizations have done throughout history, their cities, ports, and monuments would now rest on the seafloor, invisible to land-based archaeological surveys but potentially preserved in ways that land sites never could be. The rapid submersion caused by post-glacial flooding would have buried these sites under protective layers of sediment, creating time capsules that could preserve organic materials, delicate structures, and technological artifacts for thousands of years. The most dramatic example of this lost world is Doggerland, a vast landmass that once connected Britain to continental Europe. During the last ice age, this region encompassed an area larger than modern Britain, featuring rolling hills, river valleys, and extensive coastal plains. It was a paradise for Mesolithic hunter-gatherers, with rich hunting grounds, abundant freshwater sources, and strategic locations for trade and travel. But as the ice sheets melted and sea levels rose, Doggerland gradually disappeared beneath the North Sea, taking with it any evidence of the peoples who once called it home. The final catastrophe came approximately 8,200 years ago when the Storegga submarine landslide off the coast of Norway triggered a massive tsunami that swept across what remained of Doggerland, completing its submersion in a matter of hours. This natural disaster, one of the largest known prehistoric tsunamis, would have buried any surviving settlements under meters of sediment and debris, perfect conditions for archaeological preservation, but only if we can figure out how to find and excavate sites hundreds of feet underwater. Recent marine archaeology has begun to reveal the extraordinary potential of underwater sites. The discovery of Pavlopetri off the coast of Greece demonstrated what perfect preservation looks like in marine environments. This Bronze Age city, submerged approximately 5,000 years ago, retained its urban layout with such fidelity that archaeologists could map individual buildings, streets, and public spaces. The anaerobic conditions on the seafloor had prevented the bacterial decay that destroys organic materials on land, preserving wooden artifacts, textiles, and other delicate materials that would have vanished within decades in terrestrial environments. Even more spectacular was the discovery of Thonis Heraklion, the lost Egyptian port city that served as the gateway to Egypt for Mediterranean trade. Submerged by earthquakes and rising sea levels approximately 1,200 years ago, the city was rediscovered in 2001, preserved in remarkable detail. Massive pharaoh statues still stood in temple courtyards, ships rested at their ancient moorings with their cargoes intact, and inscribed stone tablets preserved records of ancient commercial transactions. The rapid submersion had created a snapshot of ancient life frozen in time, protected by the sea from the ravages of weather, vandalism, and urban development that would have destroyed similar sites on land. These confirmed discoveries represent just the beginning of oceanic archaeological potential. Commercial fishing operations regularly dredge up artifacts from the North Sea, including prehistoric tools, mammoth tusks, and human remains that confirm extensive human habitation of the now-submerged Doggerland. Dutch beaches yield a steady stream of archaeological materials washed ashore from underwater sites, including Neanderthal tools and the remains of extinct megafauna that shared the landscape with early humans. But the preservation potential of marine environments extends far beyond these relatively recent sites. Deep ocean sediments accumulate in continuous layers that can preserve evidence for millions of years with exceptional temporal resolution. Unlike terrestrial environments where erosion, bioturbation, and geological upheaval constantly disturb and destroy evidence, abyssal plains maintain stratified deposits that create precise chronological records. Ocean sediment cores can provide year-by-year records of ancient conditions, preserving evidence of atmospheric composition, climate changes, and even cosmic events like asteroid impacts or supernova explosions. The technical challenges of deep water archaeology are formidable, but advancing technology is making previously impossible investigations feasible. Remotely operated vehicles, ROVs, can now operate at depths exceeding 6,000 meters, equipped with high-resolution cameras, sample collection arms, and sophisticated analytical instruments. Autonomous underwater vehicles, AUVs, can survey vast areas of seafloor with sonar precision that rivals the best land-based archaeological mapping techniques. Side-scan sonar can detect buried structures and anomalies beneath sediment layers, while sub-bottom profilers can peer deeper into geological formations to identify potential archaeological sites. Perhaps most intriguingly, recent advances in marine geology have revealed that certain areas of the ocean floor offer exceptional preservation conditions for archaeological materials. Anoxic basins, where deep water contains no dissolved oxygen, create environments where organic materials can survive for thousands of years without decay. Cold seep areas, where hydrocarbons leak from the seafloor, can create natural preservation zones where bacterial activity is suppressed. Underwater caves and overhangs can protect sites from sediment burial while maintaining the stable conditions necessary for long-term preservation. The implications for detecting truly ancient technological civilizations become staggering when we consider the scale of oceanic preservation. If an advanced civilization had existed millions of years ago, their most durable installations would likely have been located along coastlines, ports, industrial facilities, and urban centers that depended on marine resources and trade routes. The gradual or catastrophic submersion of these sites would have created preservation conditions far superior to anything available on land. Modern research into marine sediment cores has already revealed evidence of rapid environmental changes that might indicate technological activity. Cores from the Mediterranean show sudden spikes in metal concentrations that correlate with known periods of ancient mining and smelting. Deep Atlantic cores preserve volcanic ash layers from eruptions thousands of years ago, demonstrating the fidelity with which ocean sediments record planetary events. The detection of microplastics in sediment cores dating back to the 1940s proves that even synthetic materials can be preserved and tracked through marine geological records. The search for ancient chemical signatures in ocean sediments offers perhaps our best hope for detecting prehistoric technological civilizations. Marine environments integrate signals from entire continental drainage basins, concentrating and preserving evidence of industrial activity from vast geographic regions. A civilization that engaged in large-scale mining, smelting, or fuel burning would create chemical signatures that would be recorded in marine sediments forming contemporaneously around the world. These signals would be preserved in ocean basins that might remain geologically stable for tens of millions of years. Current ocean drilling programs, originally designed to study Earth's climate history and geological processes, have inadvertently created the infrastructure for searching for technological signatures in deep time. Sediment cores spanning millions of years already exist in research repositories, waiting for analysis with techniques specifically designed to detect artificial chemical signatures. The reanalysis of existing cores using new methods could potentially reveal evidence of ancient industrial activity without requiring expensive new drilling expeditions. But perhaps the most sobering aspect of oceanic archaeology is what it reveals about the scale of our ignorance. Every underwater discovery forces us to revise our estimates of ancient human capabilities and population densities. The sophisticated urban planning of Pavle Petri, the monumental architecture of submerged temples in the Mediterranean, and the extensive landscape modifications revealed in now-flooded coastal areas all demonstrate that prehistoric societies were far more complex and capable than land-based archaeology had suggested. If sites just a few thousand years old can remain completely unknown until accidentally discovered by modern technology, what other extraordinary achievements might lie hidden beneath the waves? If relatively shallow coastal waters can conceal entire cities, what secrets might be preserved in the deep ocean basins that have remained undisturbed for millions of years? The ocean's secret archives stretch back through geological time, holding records that span not just human history, but the entire story of life on Earth. Somewhere in these vast underwater repositories might lie the chemical fingerprints we seek, evidence of technological civilizations that rose and fell long before the first human ancestor ever glimpsed the sea. The challenge lies not in preserving the evidence, for the ocean has already done that job with unparalleled efficiency, but in developing the technological and analytical capabilities to read the records it has so faithfully maintained. Mass extinction signatures. Reading planetary trauma. While the ocean's archives preserve individual moments in Earth's history with remarkable fidelity, there are certain events so catastrophic that they leave their mark not just in sediment cores or coastal deposits, but in the very chemistry of the planet itself. These are the mass extinctions, planetary-scale catastrophes that have punctuated Earth's history like exclamation points written in stone and bone. What makes these ancient disasters particularly relevant to our search for lost civilizations is a disturbing realization. The chemical signatures of these natural catastrophes bear an unsettling resemblance to the changes that modern technological civilization is currently inflicting on our planet. Earth has experienced 5 major mass extinctions over the past 540 million years, each one eliminating vast numbers of species and fundamentally reshaping the trajectory of life on our planet. But what transforms these ancient tragedies into potential Rosetta Stones for detecting technological civilizations is the growing understanding that extinction events don't just kill. They leave behind distinctive chemical fingerprints that can persist in the geological record for hundreds of millions of years. The most devastating of these ancient catastrophes, the Permian-Triassic extinction 252 million years ago, offers perhaps the clearest template for understanding how planetary-scale disasters manifest in the geological record. Known to paleontologists as the Great Dying, this event eliminated approximately 95% of all marine species and 75% of terrestrial species, the closest life on Earth has ever come to complete annihilation. Recent research has revealed that this ancient catastrophe was accompanied by atmospheric carbon dioxide concentrations that rose sixfold, from approximately 426 parts per million to over 2,500 parts per million, within a geological eye blink of roughly 75,000 years. This massive carbon release created sharp negative shifts in carbon isotope ratios of 4 to 7 parts per thousand globally, signatures so dramatic that they can be detected in rock formations on every continent. The chemical evidence suggests that between 3,900 and 12,000 gigatons of carbon were added to the atmosphere during this period, a quantity comparable to the projected impact of burning all accessible fossil fuel reserves on modern Earth. What makes these findings so unsettling is how closely they mirror the changes that industrial civilization is currently producing. Modern atmospheric carbon dioxide levels have risen from pre-industrial concentrations of 280 parts per million to over 420 parts per million in just 2 centuries, with the rate of increase accelerating dramatically. Current isotopic shifts in atmospheric carbon already measure approximately 1 part per thousand, and climate models suggest that unchecked fossil fuel burning could produce isotopic excursions of 3 to 6 parts per thousand signatures virtually indistinguishable from those left by the Great Dying. But the Permian-Triassic extinction reveals more than just carbon signatures. The event was accompanied by massive metal enrichment patterns in marine sediments, evidence of widespread ocean acidification, distinctive patterns of sulfur isotope changes, and the formation of unusual mineral assemblages that have no modern analogs. Most ominously, the extinction was preceded by a period of apparent environmental stress and declining biodiversity, warning signs that modern ecologists recognize with growing alarm in contemporary ecosystems. The key insight for detecting ancient technological civilizations lies in understanding how these natural extinction signatures differ from those that might be produced by technological activity. While volcanic eruptions and other natural processes can release massive quantities of carbon dioxide, they typically produce isotopic signatures that reflect the deep Earth sources of the carbon. Industrial burning of fossil fuels, by contrast, releases carbon that has been isotopically depleted by ancient biological processes, creating distinctive signatures that can be distinguished from volcanic sources through careful analysis. Modern research into the Anthropocene, the proposed geological epoch defined by human impact, has begun to reveal just how distinctive technological signatures actually are. Current rates of carbon dioxide increase occur roughly 250 times faster than post-ice age natural increases, creating atmospheric changes that are unprecedented in the entire geological record. Ice core data spanning 800,000 years shows that pre-industrial carbon dioxide levels remained remarkably stable around 280 parts per million for millennia, while current levels represent conditions not seen since the Pliocene epoch over 3 million years ago. Even more telling are the synthetic isotope signatures that modern technology has scattered across the planet. Nuclear weapons testing has created radioactive markers that will remain detectable in sediment cores for millennia, with isotope ratios that provide precise fingerprints of technological activity. These artificial radionuclides have no natural sources on Earth's surface, making them unambiguous markers of technological civilization, signatures so distinctive that they would immediately alert any future geologist to the presence of intelligent activity. The distribution patterns of these modern technological markers reveal something crucial about how civilization-scale signatures propagate through planetary systems. Plutonium isotopes from nuclear testing now appear in sediment cores from both polar regions, from deep ocean basins, and from lakes on every continent. The global scale of this contamination means that evidence of technological activity gets recorded simultaneously in depositional environments all over the world, dramatically increasing the probability that some record would survive even if most sites were later destroyed by geological processes. But perhaps the most significant insight from studying mass extinction chemistry is how multiple signatures combine to create distinctive patterns that are virtually impossible to produce through natural processes alone. The Permian-Triassic extinction shows carbon isotope excursions, metal enrichments, ocean acidification markers, and extinction patterns all occurring together within a relatively short time frame. While any individual signature might be explained by natural causes, the simultaneous occurrence of multiple anomalies creates a fingerprint that points unambiguously to a specific type of catastrophic event. A hypothetical ancient technological civilization that had triggered its own extinction through industrial activity would likely leave behind a similar combination of signatures: carbon isotope excursions from fossil fuel burning, metal enrichment patterns from mining and smelting, synthetic chemical signatures from industrial processes, distinctive extinction patterns reflecting habitat destruction and pollution, and potentially artificial radionuclides from nuclear technology. The combination of these signals would create a technological fingerprint that could be distinguished from natural catastrophes through careful analysis. Ocean sediment cores provide the ideal medium for detecting such ancient technological signatures because marine environments integrate signals from entire continental drainage systems. A civilization that engaged in large-scale industrial activity would create chemical anomalies that would be recorded in marine sediments forming contemporaneously around the world. These signals would be preserved in sedimentary sequences that could remain geologically stable for tens of millions of years. Current research into ancient extinction events has already begun to reveal chemical anomalies that don't fit conventional models. Some carbon isotope excursions appear to occur more rapidly than can be explained by known volcanic processes. Certain metal enrichment patterns in ancient sediments seem too concentrated and too widespread to result from normal weathering processes. While these anomalies almost certainly have natural explanations that we simply haven't identified yet, they demonstrate that our understanding of ancient environmental processes remains incomplete. The study of modern extinction processes provides additional templates for recognizing technological signatures. The current biodiversity crisis, often called the sixth mass extinction, is producing distinctive patterns that differ markedly from natural extinction events. Human-caused extinctions tend to eliminate large-bodied species first, create fragmented rather than gradual extinction patterns, and are associated with specific types of environmental degradation. These patterns would be detectable in the fossil record and could potentially distinguish technological from natural extinction causes even millions of years in the future. Perhaps most sobering is what mass extinction research reveals about the speed with which planetary systems can change. The Permian-Triassic extinction appears to have unfolded over just tens of thousands of years, rapid by geological standards, but potentially representing multiple generations of a technological civilization. This suggests that even relatively brief periods of intensive industrial activity could leave permanent markers in the geological record. The implications extend beyond academic curiosity. As our own civilization grapples with climate change, biodiversity loss, and environmental degradation, the study of ancient extinction events provides crucial insights into how planetary systems respond to rapid environmental changes. If previous technological civilizations faced similar challenges and failed, their fate might offer crucial lessons for our own survival. Modern analytical techniques can detect isotopic signatures and trace element concentrations with extraordinary precision, often measuring changes of just a few parts per million in billion-year-old rocks. This analytical power means that if ancient technological civilizations did exist and did leave chemical signatures, we now have the tools to detect them. The challenge lies not in measurement capability, but in knowing where to look and how to distinguish technological from natural signals. The mass extinction record suggests that if such signatures exist, they would most likely be found in sedimentary sequences that record periods of rapid environmental change. The chemical fingerprints of ancient disasters provide a template for the types of signals we should seek, combinations of isotopic, elemental, and synthetic chemical anomalies that occur together in ways that natural processes cannot easily explain. As we examine the scars left by Earth's greatest catastrophes, we're forced to confront an unsettling possibility. Somewhere in the chemical chaos of ancient extinction events might lie the signatures of civilizations that, like us, grew too successful for their own good and left behind only their chemical ghosts as warnings to those who would follow. Modern civilizations' future fossils. As we contemplate the chemical ghosts of ancient catastrophes and the possibility that previous civilizations might have written their own epitaphs in the geological record, a sobering question emerges. What legacy will our own technological civilization leave behind? If humanity were to vanish tomorrow, what traces would remain to puzzle future archaeologists millions of years hence? The answer reveals not only the remarkable persistence of certain technological signatures, but also provides crucial insights into what we should be looking for when searching the deep past for evidence of civilizations that may have preceded us. Unlike our ancestors who worked primarily with wood, stone, and organic materials that decay within centuries, modern industrial civilization has unleashed an unprecedented flood of synthetic materials and artificial isotopes that will persist in the geological record for millions of years. We have become, without fully realizing it, the most prolific creators of future fossils in Earth's history, writing our technological signature into the planet's rock record with a permanence that will outlast our cities, our monuments, and quite possibly our species itself. The most visible and perhaps most alien of our future fossils are plastics. Since mass production began in the 1950s, humanity has manufactured over 9 billion tons of plastic materials, synthetic polymers that have no natural analogs in Earth's 4.56 billion-year history. Recent research into microplastic preservation reveals just how permanent these materials actually are. Sediment cores from the Mediterranean Sea show plastic mass distributions that directly mirror global production from 1965 to 2016, with no detectable degradation over more than half a century of burial in marine environments. The anaerobic conditions in deep sedimentary environments dramatically slow the microbial breakdown of synthetic polymers, and emerging research suggests that some plastic degradation products may actually persist longer than the original materials. Under the right preservation conditions, plastic fragments could remain recognizable for millions of years, creating what researchers have termed technofossils. Artificial materials so distinctive that they would immediately signal the presence of technological civilization to any future investigator. Even more dramatic are the entirely novel rock types that industrial processes have created. Plastiglomerates, formed by the fusion of plastic debris with natural sediments at high temperatures, represent geological formations that could only have been created by technological activity. These hybrid materials combine natural sand, shells, and rock fragments with synthetic polymers, creating composite formations unlike anything in the natural world. Found everywhere from volcanic islands to urban beaches, plastiglomerates have become so widespread that geologists now recognize them as characteristic markers of the Anthropocene epoch. But plastics represent just the beginning of our synthetic legacy. Industrial chemistry has created over 140,000 synthetic compounds that have been released into the environment, molecular structures that have never existed in Earth's history. Many of these compounds prove remarkably persistent in natural systems. Perfluorinated chemicals can survive for thousands of years in groundwater. Persistent organic pollutants like PCBs accumulate in sediments and remain detectable for centuries. Synthetic steroids display non-biological chirality patterns that distinguish them clearly from natural compounds, creating molecular fingerprints that could persist indefinitely under appropriate conditions. Perhaps most permanent of all are the radioactive signatures that nuclear technology has scattered across the planet. Modern nuclear weapons testing has created global stratigraphic markers that will remain detectable for millennia. Plutonium isotopes, with their distinctive ratios that vary depending on the source and type of nuclear device, now appear in sediment cores worldwide. These artificial radionuclides have no natural sources on Earth's surface, making them unambiguous markers of technological activity, signatures so distinctive that they would immediately alert any future scientist to the presence of intelligent life. The longevity of these nuclear signatures is staggering. Plutonium-239 has a half-life of 24,100 years, meaning detectable quantities will persist for over 100,000 years. Plutonium-240 lasts even longer, while other artificial isotopes like americium-241 and cesium-137 create additional chronological markers spanning different timescales. Current research in Baltic Sea sediments demonstrates how precisely these signatures preserve. Scientists can trace the exact history of nuclear weapons testing by analyzing isotope ratios in marine sediment cores, with different combinations serving as fingerprints for specific nuclear tests and reactor accidents. Even more remarkable is plutonium-244, with its 80.8 million-year half-life. This isotope occurs naturally only in the hearts of exploding stars, making any significant terrestrial concentration conclusive evidence of technological activity. Nuclear waste repositories and reactor sites will remain radioactive for millions of years, creating permanent beacons of artificial isotopes that would be detectable across geological timescales that dwarf human civilization. The global distribution of these technological markers reveals something crucial about how civilization-scale signatures propagate through planetary systems. Industrial pollutants now appear in ice cores from both polar regions, in deep ocean sediments from every major basin, and in lake sediments on every continent. The planetary scale of this contamination means that evidence of technological activity gets recorded simultaneously in depositional environments all over the world, dramatically increasing the probability that some record would survive even if most sites were later destroyed. Metal signatures provide another category of permanent technological markers. Modern industrial civilization has fundamentally altered the global cycling of dozens of elements, creating enrichment patterns that far exceed natural background levels. Anthropogenic fluxes of lead, chromium, antimony, and platinum group metals now exceed natural sources by factors of 10 to 1,000. These metal enrichments appear in sediments worldwide and will persist as geochemical anomalies for millions of years. Mining operations alone create extraordinary signatures that dwarf anything in the natural world. Gold extraction generates between 100,000 and 1 million times more waste rock than refined metal, creating massive disturbances in natural element distributions. Copper mining moves more earth annually than all the world's rivers combined. Coal mining has altered the chemistry of vast regions through acid mine drainage and heavy metal contamination. These industrial signatures will remain detectable as anomalous metal concentrations in sedimentary sequences long after the mines themselves have been eroded away. Perhaps most intriguingly, modern civilization has created distinctive isotopic signatures in common elements through industrial processes. Lead isotope ratios in environmental samples now clearly reflect the burning of leaded gasoline, with different ratios indicating different petroleum sources and refining processes. Sulfur isotopes record the signature of coal burning and industrial sulfur processing. Even carbon isotopes in atmospheric CO2 now carry the distinctive signature of fossil fuel combustion, isotopically light carbon that clearly indicates the burning of ancient organic matter. The speed with which these signatures accumulate provides insights into how ancient technological civilizations might appear in the geological record. Many of our most distinctive markers appeared essentially instantaneously in geological terms. Nuclear isotopes appeared globally within decades of the first atomic tests. Plastic microparticles went from zero to ubiquitous in marine sediments within a single human generation. Synthetic chemical signatures show exponential increases that mirror industrial production curves. This pattern suggests that technological signatures would likely appear as sharp spikes in the geological record rather than gradual transitions. An ancient civilization's chemical footprint might be preserved as a brief but intense anomaly, a few centimeters of sediment that records thousands of years of industrial activity. The challenge for future investigators would lie not in detecting these signatures, but in recognizing them as technological rather than natural phenomena. Modern analytical techniques provide a template for the kinds of investigations that could detect ancient technological signatures. Mass spectrometry can identify individual molecules in billion-year-old rocks. Isotope ratio measurements can detect changes of just a few parts per million. Trace element analysis can map the distribution of metals with extraordinary precision. If ancient civilizations left chemical signatures, we now have the analytical power to find them. The preservation potential varies dramatically by environment and material type. Marine sediments offer the best long-term preservation, particularly in deep ocean basins and anoxic environments where bacterial activity is suppressed. Organic materials face rapid degradation in most environments, but synthetic polymers and metal alloys can survive much longer. Nuclear isotopes and distinctive metal concentrations represent the most persistent signatures, potentially surviving tens of millions of years under appropriate conditions. But perhaps the most sobering insight from studying our own technological signatures is how rapidly they accumulate and how clearly they mark the transition from pre-industrial to technological civilization. The chemical composition of Earth's atmosphere, oceans, and sediments has changed more in the past century than in the previous millennium. We are conducting a real-time experiment in planetary transformation, creating signatures that will persist long after our civilization has crumbled to dust. These modern signatures provide crucial insights into what we should look for when searching for ancient technological civilizations. Rather than expecting to find cities or artifacts, we should focus on chemical anomalies. Unusual isotope ratios, artificial compounds, metal enrichments, and extinction patterns that occur together in ways that natural processes cannot easily explain. The key lies in recognizing combinations of signatures that create technological fingerprints distinguishable from natural phenomena. Our own civilization's future fossils will include layer upon layer of plastic debris, radioactive isotopes scattered across the globe, synthetic chemicals that never existed before, and metal concentrations that exceed anything in the natural world. These markers will persist in the geological record as monuments to human technological achievement, and as templates for recognizing similar signatures that previous civilizations may have left in the deep past. When nature reclaims the world, while our chemical signatures may persist for millions of years as permanent monuments to technological civilization, the physical structures we build, Our cities, roads, and monuments that seem so solid and enduring tell a very different story about permanence and time. To understand how quickly the tangible evidence of civilization can vanish, we need look no further than the abandoned places scattered across our modern world, where nature has begun the inexorable process of reclaiming what humanity built. These contemporary ruins offer a sobering preview of what future archaeologists might find when they search for traces of our civilization, and more importantly, they provide crucial insights into why the physical evidence of ancient technological societies might have vanished so completely from the archaeological record. The most dramatic and haunting example of this process unfolds in the forests of northern Ukraine, where the city of Pripyat stands as an accidental monument to civilization's fragility. On April 26, 1986, the explosion at the nearby Chernobyl nuclear power plant forced the evacuation of Pripyat's 50,000 residents within 36 hours. In that single day, a thriving Soviet city became a ghost town, and in the decades since, nature has transformed this urban landscape into something that resembles a post-apocalyptic fantasy more than the planned community it once was. Walking through Pripyat today, nearly 4 decades after the evacuation, visitors encounter scenes that seem to defy belief. Birch trees now grow through the windows of 8th-floor apartments, their roots having found purchase in the concrete and gradually splitting apart the building's structure. The city's swimming pool, once a centerpiece of community recreation, has become a wetland where frogs breed in the stagnant water while vegetation pushes up through cracks in the pool deck. The iconic Ferris wheel in the amusement park, never operational before the disaster, stands rusted and overgrown, its yellow gondolas now home to birds and small mammals. What makes Pripyat's transformation so scientifically valuable is the precise timeline it provides. We can observe exactly how quickly different materials and structures succumb to natural forces when human maintenance stops. Within the first decade, vegetation began colonizing rooftops and courtyards. By the second decade, trees were establishing themselves in building foundations, and their roots were beginning to crack concrete and asphalt. Now, approaching the fourth decade, entire buildings show structural damage from plant growth, and some smaller structures have been completely overwhelmed by forest regrowth. The city has become Europe's largest unintentional nature preserve, hosting over 60 mammal species, including wolves at 7 times the population density of neighboring reserves. Brown bears, lynx, and elk roam streets where children once played. Wild boar root through abandoned gardens, while more than 200 bird species nest in the ruins of Soviet apartment blocks. Perhaps most remarkably, Przewalski's horses, reintroduced to the exclusion zone in the late 1990s, have multiplied 7-fold and now gallop freely through radioactive forests that have become their sanctuary. The Pripyat example reveals a crucial principle. Despite radiation levels that remain dangerous to humans, the absence of human activity has proven more beneficial to ecosystem recovery than nuclear contamination has been harmful. This suggests that abandoned technological sites might be preferentially colonized by nature, accelerating the destruction of physical evidence while potentially preserving chemical signatures in the soil and sediments. But Pripyat is not unique in demonstrating nature's remarkable efficiency at reclaiming human settlements. Across the globe, abandoned cities and industrial sites tell similar stories of rapid ecological succession and structural decay. Hashima Island in Japan, abandoned in 1974 when its coal mines closed, now resembles a concrete reef where seabirds nest in the ruins of apartment buildings and salt spray corrodes the reinforced structures that once housed 5,000 residents. The buildings show dramatic deterioration from just 5 decades of abandonment, with concrete spalling, steel reinforcement rusting, and vegetation establishing itself in every crack and crevice. In the Namib Desert, the diamond mining town of Kalmanskap was abandoned in the 1950s and is now being consumed by sand dunes that flow through the buildings like a slow-motion flood. The dry conditions have preserved some structures better than those in wetter climates. Yet even here, the buildings are gradually succumbing to the relentless accumulation of sand and the expansion and contraction caused by extreme temperature variations. Perhaps most relevant to understanding the fate of technological civilizations are the urban ruins found in more temperate climates. Detroit, Michigan, provides a particularly sobering example of how quickly modern infrastructure can deteriorate when economic forces lead to widespread abandonment. Entire neighborhoods show advanced stages of decay after just decades of reduced maintenance, with trees growing through the roofs of houses, vegetation reclaiming streets and parking lots, and nature transforming industrial sites into accidental wetlands. The abandoned automobile plants of Detroit reveal how quickly even massive industrial structures can succumb to natural forces. The Packard automotive plant, closed in 1958, has become a vertical forest where trees grow from upper-story floors, their roots having found pathways through the concrete and steel structure. Rain infiltration has accelerated the decay process, causing concrete to spall and steel reinforcements to rust and expand, further damaging the building's integrity. Similar patterns appear worldwide. In China, the fishing village of Hutuan was abandoned in the 1990s due to economic changes, and within just 3 decades, the entire settlement has been consumed by vegetation. Houses are completely overgrown with ivy and other climbing plants, creating green mounds that barely hint at the structures beneath. The speed of this transformation, occurring within a single human generation, demonstrates how quickly tropical and subtropical vegetation can obliterate architectural evidence. These modern examples reveal several crucial insights about preservation and destruction processes. Organic materials disappear first and fastest. Wood rots, fabric disintegrates, and paper crumbles within years of abandonment. Metals face rapid corrosion, particularly iron and steel, which rust and expand when exposed to moisture, accelerating structural collapse. Even concrete, which seems so permanent, proves vulnerable to freeze-thaw cycles, plant root growth, and chemical weathering that can reduce massive structures to rubble within decades. But the most insidious destroyer of architectural evidence is vegetation itself. Plant roots follow the smallest cracks and crevices, exerting tremendous pressure as they grow and gradually splitting apart even the most solid construction. Trees establish themselves on rooftops, their roots eventually penetrating building foundations and their weight causing structural failures. Moss and lichens create acidic conditions that accelerate the chemical breakdown of stone and concrete surfaces. The biological processes operating in these abandoned sites also reveal something crucial about what does persist when civilizations collapse. While buildings crumble and infrastructure fails, the soil beneath becomes enriched with distinctive chemical signatures. Heavy metals from industrial processes, synthetic compounds from manufacturing, and unusual isotope ratios from technological activities accumulate in the ground and persist long after the structures that created them have vanished. Studies of soil chemistry in abandoned industrial sites reveal contamination patterns that remain detectable decades or centuries after the original activity ceased. Lead from automotive emissions, mercury from industrial processes, and synthetic organic compounds from manufacturing create distinctive geochemical signatures that could theoretically persist for thousands or even millions of years under appropriate preservation conditions. The speed of architectural decay also varies dramatically with climate and material composition. In tropical environments, vegetation can completely consume buildings within decades, while biological activity accelerates the decay of organic materials. In arid environments, structures may persist much longer, but sandblasting and extreme temperature variations create different destruction mechanisms. In cold climates, freeze-thaw cycles prove particularly destructive to masonry and concrete, while permafrost can actually preserve certain materials for extended periods. Underground infrastructure shows greater persistence than surface structures, but even this proves vulnerable over extended time periods. Sewage systems and subway tunnels can survive for centuries when sealed from water infiltration, but they too eventually succumb to groundwater intrusion, soil pressure, and chemical degradation. Roman sewers and aqueducts provide examples of impressive longevity, but these represent exceptional preservation cases rather than typical outcomes. The implications for detecting ancient technological civilizations become clear when we extrapolate these decay processes over millions of years. Even the most massive and durable structures would eventually crumble to unrecognizable rubble, while smaller artifacts would simply vanish. Only the most chemically stable materials, certain ceramics, glass, precious metals, and synthetic compounds, would have any chance of surviving recognizable over geological timescales. This explains why the search for ancient civilizations must focus on chemical rather than physical evidence. While our cities may seem eternal from a human perspective, they are ephemeral on geological timescales. The concrete and steel monuments to our technological achievement will eventually become soil enriched with unusual chemical signatures. Just as any previous technological civilization, cities would have become indistinguishable components of the geological record. The abandoned places of our modern world serve as laboratories for understanding these processes, revealing both the remarkable speed with which nature reclaims technological landscapes and the types of signatures that persist long after the structures themselves have vanished. They remind us that civilizations may be temporary, but their chemical ghosts can haunt the earth for millions of years. Invisible monuments waiting to be discovered by those clever enough to read the language written in stone and soil. The deep time detectives. As we contemplate the chemical ghosts that outlast the physical monuments of vanished civilizations, a new generation of scientists has emerged, armed with technologies that would seem like magic to archaeologists of just a few decades ago. These deep time detectives are revolutionizing our ability to read the language written in stone and soil, developing methods so sophisticated that they can detect the faintest traces of ancient activity across millions of years. Their tools reach into the Earth's most secret archives, pierce through dense jungle canopies, and analyze chemical signatures with precision that borders on the supernatural. For the first time in human history, we possess the technological capability to systematically search for evidence of prehistoric technological civilizations, and the results are already reshaping our understanding of what lies hidden in our planet's past. The revolution began with light itself, specifically with laser light that can see through solid vegetation and map the hidden landscapes beneath. Light detection and ranging technology, known as LiDAR, fires millions of laser pulses at the ground from aircraft or satellites, measuring the time it takes for each pulse to return and creating three-dimensional maps of extraordinary precision. What makes this technology revolutionary for archaeology is its ability to penetrate forest canopies and reveal structures that have been hidden for centuries or millennia. The impact has been nothing short of extraordinary. In the jungles of Guatemala, LiDAR surveys have uncovered over 60,000 previously unknown Maya structures, revealing a civilization far more complex and extensive than anyone had imagined. What archaeologists thought were scattered settlements turned out to be components of vast urban networks spanning hundreds of square kilometers, connected by sophisticated road systems and supported by elaborate water management infrastructure. The technology revealed not just buildings, but entire landscapes modified by human activity, terraced hillsides, drained wetlands, and defensive fortifications that completely transformed our understanding of pre-Columbian America. But LiDAR's most profound contribution to the search for ancient civilizations may be its ability to detect subtle landscape modifications that could indicate technological activity. When massive construction projects alter natural drainage patterns, create artificial mounds, or establish geometric landscape features, these changes leave permanent signatures in the topography that can persist for thousands or even millions of years. Advanced LiDAR analysis can now detect elevation changes as small as a few centimeters across vast areas, potentially revealing the ghostly outlines of ancient industrial sites, mining operations, or urban centers long after every trace of surface construction has vanished. The Amazon basin has become a particularly rich hunting ground for LiDAR archaeologists. Surveys have revealed massive geometric earthworks, precise geometric patterns carved into the landscape over areas spanning thousands of square kilometers. These geoglyphs, created by pre-Columbian peoples, demonstrate mathematical knowledge and engineering capabilities that challenge every assumption about prehistoric Amazonian societies. Most remarkably, many of these structures were only discovered in recent decades, hidden beneath forest canopies that had concealed them for centuries. Working in partnership with LiDAR technology, artificial intelligence has begun to revolutionize the detection of archaeological sites. Machine learning algorithms trained on known archaeological features can now scan satellite imagery and LiDAR data with superhuman speed and accuracy, identifying potential sites that human researchers might overlook. These AI systems have achieved 80% accuracy in identifying potential archaeological sites across vast geographical areas, enabling systematic surveys of previously inaccessible regions. The power of AI extends beyond simple pattern recognition. Deep learning networks can identify subtle combinations of topographical, vegetational, and geological features that correlate with hidden archaeological sites. They can detect the faint rectangular outlines of buried foundations, recognize the characteristic vegetation patterns that grow above disturbed soil, and identify the subtle color variations in satellite imagery that indicate subsurface archaeological deposits. Most intriguingly, these systems are beginning to identify types of landscape modifications that don't match any known archaeological patterns, anomalies that might indicate previously unknown forms of ancient human activity. Underwater archaeology has experienced its own technological revolution through advanced sonar mapping and robotic exploration systems. Modern side-scan sonar can create three-dimensional maps of the ocean floor with resolution approaching that of aerial photography, while sub-bottom profiling sonar can peer through sediment layers to reveal buried structures and geological anomalies. Autonomous underwater vehicles equipped with sophisticated sensor arrays can now survey vast areas of seafloor, searching for the geometric patterns and unusual material concentrations that might indicate ancient technological activity. The recent discovery of sophisticated Bronze Age settlements on the European continental shelf demonstrates the power of these underwater detection methods. High-resolution sonar mapping has revealed entire preserved landscapes that were submerged by post-glacial flooding, complete with ancient river channels, settlement sites, and evidence of extensive human modification of the environment. These finds suggest that vast areas of the continental shelf may contain perfectly preserved archaeological sites dating back thousands of years, and potentially much longer. But perhaps the most powerful tools in the Deep Time Detective's arsenal are the analytical techniques that can detect chemical signatures with almost unimaginable precision. Modern mass spectrometry can identify individual molecules in billion-year-old rocks, while isotope ratio measurements can detect changes of just a few parts per million in elemental compositions. These techniques are sensitive enough to detect the chemical fingerprints of ancient industrial activity even when those signatures have been diluted across geological timescales. Accelerator mass spectrometry has revolutionized the detection of trace isotopes, enabling researchers to measure concentrations of artificial radionuclides at levels thousands of times lower than previous techniques could achieve. This technology could theoretically detect plutonium signatures from ancient nuclear technology even after millions of years of radioactive decay, providing unambiguous evidence of technological activity across geological timescales. Advanced geochemical analysis now routinely detects anthropogenic signatures in sediment cores dating back thousands of years. Researchers can trace the history of ancient mining operations through metal enrichment patterns, identify periods of intensive agriculture through changes in erosion rates and soil chemistry, and even detect the signatures of early metallurgy through distinctive lead isotope ratios. These techniques provide templates for the types of signatures that much older technological civilizations might have left behind. The integration of multiple analytical techniques has proven particularly powerful. When researchers combine carbon isotope analysis with metal concentration measurements, synthetic compound detection, and biomarker analysis, they can create detailed pictures of ancient environmental conditions and human activities. This multi-proxy approach could potentially distinguish technological from natural signatures even when individual measurements might be ambiguous. Satellite-based detection systems have opened entirely new avenues for archaeological prospection. Hyperspectral imaging can detect subtle differences in surface mineralogy that indicate buried archaeological deposits, while thermal infrared imaging can reveal subsurface structures through their differential heat retention properties. These space-based systems can survey entire continents systematically, searching for the types of landscape anomalies that might indicate ancient technological activity. Ground-penetrating radar technology has advanced to the point where it can map subsurface structures with extraordinary detail without disturbing the overlying deposits. Modern systems can penetrate dozens of meters into the ground and create three-dimensional images of buried features with centimeter-scale resolution. This technology could potentially detect the foundations of ancient structures, unusual subsurface material concentrations, or geometric patterns that indicate technological activity. The development of portable analytical equipment has democratized the search for chemical signatures of ancient civilizations. Handheld X-ray fluorescence spectrometers can now measure elemental compositions in real time in the field, while portable mass spectrometers can identify organic compounds and isotope ratios without laboratory analysis. These tools enable researchers to conduct preliminary surveys of vast areas and identify locations that warrant more detailed investigation. Perhaps most intriguingly, researchers are beginning to apply techniques originally developed for detecting modern environmental contamination to the search for ancient technological signatures. Methods for tracking industrial pollution in modern sediments can be adapted to search for similar patterns in ancient deposits. Techniques for detecting synthetic organic compounds in groundwater can be modified to search for evidence of ancient chemical manufacturing. The analytical methods developed to study the Anthropocene may provide the keys to detecting earlier technological epochs. The convergence of these technologies is creating unprecedented opportunities for systematic searches for ancient technological civilizations. For the first time, researchers can survey vast areas with high precision, detect chemical signatures across geological timescales, and analyze data with computational power that can identify patterns invisible to human investigators. The combination of space-based surveying, advanced analytical chemistry, artificial intelligence, and robotic exploration systems provides tools that are finally adequate to the scale of the search. Current research programs are beginning to implement systematic searches for technological signatures in the geological record. Projects like the NASA Astrobiology Initiative and the SETI Institute's Technosignature Research are developing standardized methodologies for detecting evidence of technological activity across multiple timescales. These efforts combine geological surveying, geochemical analysis, and computational modeling to create comprehensive frameworks for identifying technological signatures. The implications extend far beyond the search for ancient terrestrial civilizations. The same techniques being developed to detect technological signatures in Earth's geological record are being adapted for the search for evidence of technological civilizations on other planets. Methods for detecting atmospheric pollution on exoplanets, identifying unusual surface modifications on Mars, and recognizing technological signatures in astronomical observations all build upon research into detecting ancient technological activity on Earth. As these deep time detectives continue to refine their methods and expand their searches, they are fundamentally changing our understanding of what can be detected across geological timescales. Their tools have already revealed that the Earth holds far more secrets than we ever imagined, and that human technological capability extends much further into the past than conventional archaeology suggested. Whether these methods will eventually uncover evidence of truly ancient technological civilizations remains an open question, but the search itself is revolutionizing our understanding of Earth's deep history and humanity's place within it. The skeptic's arsenal. Yet, for all the technological wizardry that modern deep time detectives bring to their search, for all the sophisticated analytical techniques that can detect chemical signatures across millions of years, and despite the revolutionary discoveries that continue to reshape our understanding of ancient human capabilities, the vast majority of mainstream scientists remain deeply skeptical about the existence of technologically advanced prehistoric civilizations. This skepticism is not born of closed-mindedness or academic conservatism, but from a rigorous evaluation of evidence that consistently reveals conventional explanations for even the most mysterious archaeological anomalies. The skeptic's arsenal, built from decades of careful investigation and scientific methodology, provides a sobering counterpoint to speculation about lost civilizations, and in doing so, actually strengthens and refines our search for genuine evidence of ancient technological activity. The foundation of scientific skepticism rests on a principle that has served science well for centuries. Extraordinary claims require extraordinary evidence. The suggestion that advanced technological civilizations existed millions of years before humans represents one of the most extraordinary claims possible, demanding evidence that meets the highest standards of scientific rigor. When subjected to this scrutiny, even the most compelling apparent anomalies in the archaeological and geological records have consistently yielded to conventional explanations that require no revolutionary revisions to our understanding of Earth's history. Consider the most prominent contemporary advocate for ancient advanced civilizations, journalist Graham Hancock, whose theories about a lost civilization destroyed by cosmic impact 12,000 years ago have captured popular imagination through best-selling books and Netflix documentaries. When Hancock's claims are subjected to rigorous scientific analysis, they reveal fundamental methodological problems that illustrate why mainstream archaeology remains unconvinced. The proposed comet impact that supposedly destroyed this ancient civilization lacks the most basic evidence that such an event would necessarily leave behind. No impact crater of appropriate age has been identified, despite the fact that impacts large enough to cause global catastrophe inevitably create geological scars that persist for millions of years. The radiometric dates cited as evidence for the impact actually span a range from 14,000 to 10,000 years ago, a 4,000-year spread that would be impossible if they all marked the same catastrophic event. Most tellingly, the extinction patterns attributed to this cosmic disaster are better explained by well-documented causes: human arrival in the Americas, climate change at the end of the Ice Age, and the natural process of ecological adjustment to rapidly changing environmental conditions. The archaeological evidence cited for advanced prehistoric civilization proves equally problematic under scientific scrutiny. Sites like Göbekli Tepe, while genuinely remarkable and important for understanding the development of human society, show no evidence of the technological capabilities that would characterize truly advanced civilization. The site lacks domesticated animals, metal tools, wheeled transport, writing systems, or complex urban infrastructure. What it does demonstrate is that hunter-gatherer societies were capable of far more sophisticated social organization and monumental construction than previously assumed. A significant discovery, but one that extends rather than revolutionizes our understanding of human development. The scientific community's resistance to claims about ancient advanced civilizations also stems from recognition of a persistent logical fallacy that underlies many such theories: the argument from ignorance. This fallacy assumes that if we cannot immediately explain how ancient peoples accomplished something, they must have possessed technologies beyond their supposed capabilities or received help from external sources. This reasoning reverses the burden of proof, requiring science to disprove extraordinary explanations rather than requiring proponents to provide positive evidence for their claims. Mainstream archaeology has consistently demonstrated that this approach leads to serious errors in interpretation. The construction techniques used for megalithic monuments, once considered impossibly advanced for ancient peoples, have been successfully replicated using only the tools and materials available to their builders. The astronomical knowledge reflected in ancient monuments, while impressive, falls well within the capabilities of careful long-term observation using naked-eye astronomy. The mathematical precision of structures like the Egyptian pyramids, though remarkable, can be achieved through trial-and-error methods and accumulated practical experience rather than requiring advanced theoretical knowledge. The phenomenon of out-of-place artifacts, oaparts, provides particularly clear examples of how careful scientific investigation resolves apparent anomalies. The famous Baghdad Battery, consisting of a ceramic jar, copper cylinder, and iron rod dating to ancient Mesopotamia, was initially interpreted as evidence for ancient electrical technology. Detailed analysis revealed that identical vessels appear abundantly in archaeological contexts as storage containers for sacred scrolls, produce no meaningful electrical current when assembled as proposed, and show no evidence of the electroplating processes they supposedly powered. Similarly, the Khoso artifact, discovered in California and initially claimed to be a spark plug embedded in 500,000-year-old rock, turned out to be a 1920s champion spark plug encased in rapidly forming concretionary limestone, a geological process that can occur within decades rather than millennia. The London Hammer, allegedly found embedded in ancient rock formations, represents another modern tool that became encased in rapidly forming mineral deposits. These cases illustrate a crucial aspect of scientific methodology: the importance of considering the most parsimonious explanation that accounts for all available evidence. When an artifact appears out of place chronologically, the most likely explanations involve contamination, misidentification of geological context, or misunderstanding of preservation processes rather than revolutionary revisions to human history. The scientific dating methods that form the backbone of archaeological chronology provide another powerful tool in the skeptic's arsenal. Modern dating techniques employ multiple independent methods with cross-validation requirements that make systematic errors extremely unlikely. Radiocarbon dating provides accuracy within 50 to 100 years up to 50,000 years ago, while potassium-argon dating handles older volcanic materials. Thermoluminescence dates pottery and heated materials. Dendrochronology provides annual precision for organic materials, and archaeomagnetic dating uses Earth's changing magnetic field. Significant chronological claims require confirmation through multiple independent methods with peer review by specialists in dating techniques. The taphonomic processes that determine what preserves in the archaeological record also provide clear explanations for apparent gaps and anomalies. Material bias favors preservation of hard, durable substances over organic materials. Environmental bias creates preferential preservation in specific conditions like dry caves, waterlogged sites, and permafrost. Cultural bias leads to better preservation of elite and ceremonial objects compared to everyday items. Temporal bias results in better representation of recent periods due to less time for degradation. These systematic biases explain apparent discontinuities in the archaeological record without requiring lost advanced civilizations. Perhaps most importantly, mainstream archaeology maintains rigorous standards for what constitutes evidence of advanced civilization. True technological civilization requires urban settlements with substantial permanent populations, specialized craft production beyond basic subsistence needs, extensive trade networks indicating economic complexity, clear social stratification with administrative hierarchies, monumental architecture requiring coordinated labor organization, and sophisticated agricultural systems capable of supporting non-food producing specialists. Sites proposed as evidence for ancient advanced civilizations consistently lack most or all of these characteristics. The scientific community's skepticism also reflects understanding of the extraordinary preservation challenges that face archaeological evidence across geological timescales. The same processes that make chemical signatures our best hope for detecting ancient technological civilizations also explain why physical evidence becomes vanishingly unlikely over millions of years. Less than 1% of Earth's surface consists of rocks older than 3.5 billion years, and the rocks that preserve fossils and archaeological materials represent a tiny fraction of any given time period's original surface. However, this skepticism serves a crucial constructive purpose in refining our search methods. By rigorously testing and eliminating false positives, scientific skepticism helps identify the types of evidence that would actually indicate technological activity. The debunking of spurious claims strengthens the framework for recognizing genuine anomalies when they appear. The insistence on multiple independent lines of evidence helps develop more sophisticated detection methods. Modern scientific skepticism also acknowledges that absence of evidence is not evidence of absence, particularly when dealing with phenomena that would be extremely difficult to detect. While no current evidence supports the existence of ancient technological civilizations, the scientific framework developed by researchers like Schmidt and Frank provides legitimate methodologies for systematic searches. The key lies in maintaining appropriate standards of evidence while remaining open to discoveries that meet those standards. The skeptic's arsenal ultimately serves to protect science from wishful thinking while ensuring that genuine discoveries receive appropriate recognition. The same rigorous methodology that rejects unfounded claims about ancient astronauts and lost supercivilizations also provides the tools necessary to recognize legitimate evidence of ancient technological activity, should it ever be discovered. This careful balance between skepticism and openness reflects the best traditions of scientific inquiry. While extraordinary claims about ancient civilizations continue to capture popular imagination, the scientific community's measured response ensures that when truly extraordinary evidence finally emerges, it will be recognized and evaluated with the rigor it deserves. The skeptics stand guard not against discovery, but against the premature acceptance of claims that would distort our understanding of the past and waste resources that could be directed toward genuine scientific advance. The arsenal of scientific skepticism thus serves as both a shield against unfounded speculation and a lens that focuses our attention on the types of evidence that would actually prove the existence of ancient technological civilizations, should such evidence ever be found. The final verdict: what the evidence really tells us. As our journey through the deepest mysteries of Earth's history draws to a close, we find ourselves standing at the intersection of rigorous science and profound wonder, armed with tools that can detect chemical whispers across millions of years, yet humbled by the vastness of what remains unknown. The evidence we have examined, from the sophisticated analytical frameworks of the Silurian hypothesis to the rapid reclamation of Pripyat by nature, from the impossible precision of the Antikythera mechanism to the skeptical rigor that protects science from wishful thinking, paints a complex picture that defies simple conclusions. We have not found definitive proof of ancient technological civilizations, but we have discovered something perhaps equally remarkable: that the question itself has fundamentally transformed our understanding of intelligence, time, and our place in the cosmic story. The comprehensive scientific analysis reveals a sobering truth about the challenges facing any search for truly ancient technological civilizations. The geological processes that govern our planet operate with a ruthless efficiency that erases physical evidence across the vast scales of deep time. Mountains rise and erode away, ocean floors are consumed by subduction, and even the most massive constructions of human engineering face inevitable destruction by the combined forces of chemistry, biology, and physics. The mathematical reality is unforgiving. The probability of finding direct physical evidence of technological civilizations older than a few million years approaches zero, not because such civilizations could not have existed, but because Earth simply does not preserve surface evidence across geological timescales. Yet our investigation has revealed that certain types of evidence possess remarkable persistence. Chemical and isotopic signatures can survive for millions of years under appropriate preservation conditions, creating the possibility that technological civilizations might leave detectable traces long after every physical monument has crumbled to dust. The carbon isotope excursions that could result from massive fossil fuel burning, the artificial radionuclides that have no natural terrestrial sources, the synthetic compounds that represent molecular structures unknown in Earth's 4.56 billion-year history. These signatures offer our best hope for detecting the ghostly presence of ancient technological activity. The development of the Silurian hypothesis has provided a rigorous scientific framework for this search, transforming what was once the realm of speculation into a legitimate field of scientific inquiry. Schmidt and Frank's methodology focuses on planetary-scale physical-chemical signatures rather than direct artifacts, recognizing that technological civilizations alter the chemistry of their entire planet in ways that can be distinguished from natural processes. Their framework has already influenced astrobiology research, SETI methodologies, and our understanding of how technological civilizations interact with planetary systems. Modern analytical capabilities have reached the point where, if such signatures exist, we now possess the tools to detect them. Mass spectrometry can identify individual molecules in billion-year-old rocks. Isotope ratio measurements can detect changes of just a few parts per million. Advanced imaging technologies can reveal hidden structures beneath forest canopies and ocean sediments. Artificial intelligence can recognize patterns in vast datasets that would be invisible to human investigators. For the first time in human history, we have developed technologies adequate to the scale of the search we are undertaking. The archaeological anomalies we have examined, from Göbekli Tepe's impossible timeline to the lonely sophistication of the Antikythera mechanism, reveal that human capability has consistently exceeded our expectations throughout history. These discoveries don't prove the existence of lost supercivilizations, but they demonstrate the danger of underestimating human ingenuity and the likelihood that significant achievements remain hidden in the archaeological record. They remind us that the absence of evidence is not evidence of absence, particularly when dealing with phenomena that face such extraordinary preservation challenges. The ocean's secret archives represent perhaps our greatest untapped archaeological frontier. With 98% of the seafloor lying beyond conventional exploration and vast areas of formerly exposed continental shelf now submerged beneath hundreds of feet of water, the potential for major discoveries remains enormous. The perfect preservation of sites like Pavlopetri and Thonis Heraklion demonstrates that marine environments can maintain archaeological evidence in ways that terrestrial sites cannot, potentially preserving traces of ancient civilizations that would have been destroyed on land. The study of mass extinction signatures provides templates for recognizing the types of planetary-scale disruptions that technological civilizations might cause. The chemical fingerprints of events like the Permian-Triassic extinction show how rapidly atmospheric and oceanic chemistry can change, and how these changes are preserved in the geological record for hundreds of millions of years. The similarity between these ancient catastrophes and the changes that modern industrial civilization is currently producing offers both insights into detection methods and sobering warnings about our own future. Our examination of modern civilization's future fossils reveals that we are creating chemical signatures that will persist in the geological record for millions of years. Plastic microparticles, artificial radionuclides, synthetic chemical compounds, and distinctive metal enrichment patterns will serve as permanent markers of our technological activity. These modern signatures provide crucial insights into what we should look for when searching for evidence of ancient technological civilizations, while also demonstrating the types of permanent changes that advanced civilizations inevitably inflict on their planetary environments. The rapid reclamation of abandoned human settlements by natural processes illuminates both the fragility of technological achievements and the persistence of their chemical traces. While buildings crumble and infrastructure fails within decades of abandonment, the soil beneath becomes enriched with distinctive chemical signatures that could persist for geological timescales. This pattern suggests that any ancient technological civilization would likely be detectable through geochemical analysis rather than direct archaeological evidence. Scientific skepticism has played a crucial role in refining our understanding of what would actually constitute evidence of ancient technological activity. The rigorous debunking of spurious claims and out-of-place artifacts has helped identify the types of evidence that would be both convincing and scientifically valid. This skeptical framework protects against false positives while ensuring that genuine discoveries receive appropriate recognition when they meet established standards of evidence. Yet perhaps the most profound insight from our investigation is what it reveals about the nature of intelligence and time itself. If technological intelligence has emerged once on Earth, basic probability suggests it could have emerged before. The universe operates according to physical laws that make the development of intelligence and technology not just possible, but perhaps inevitable given sufficient time and opportunity. Earth's 4.56 billion-year history provides ample opportunity for multiple experiments in intelligence, consciousness, and technological development. The implications extend far beyond academic curiosity. As our own civilization grapples with climate change, resource depletion, and environmental degradation, the question of how previous technological species might have faced similar challenges becomes urgently practical. If other civilizations have risen and fallen on Earth, their fate might offer crucial insights into the long-term viability of technological societies. The chemical signatures we are learning to detect might serve not just as evidence of ancient intelligence, but as warnings about the consequences of technological success. The search for ancient civilizations has also fundamentally changed our perspective on humanity's relationship with planetary systems. We now understand that technological civilizations inevitably become geological forces, altering the chemistry and biology of their planets in ways that persist across deep time. This realization has profound implications for how we think about our responsibilities as a technological species and our role in shaping Earth's future evolution. Whether or not ancient technological civilizations actually existed on Earth, the systematic search for their traces has advanced our understanding of planetary systems, preservation processes, and the detectability of technological signatures across multiple fields of study. The methodologies developed for this search are being applied to the detection of technological civilizations on exoplanets, the analysis of environmental changes in Earth's history, and the development of frameworks for long-term thinking about technological sustainability. The question that began our investigation, what if another civilization existed before humanity on Earth, has led us through a journey that encompasses the latest advances in analytical chemistry, the deepest mysteries of archaeology, the most sophisticated technologies for exploring hidden landscapes, and the most rigorous frameworks for evaluating extraordinary claims. We have not found definitive answers, but we have discovered that asking the question systematically has revealed new depths to our planet's capacity for secrets and new appreciation for the remarkable recent emergence of technological intelligence. In the end, we are left with a profound sense of both humility and possibility. Humility because the evidence suggests that if ancient technological civilizations did exist, they have successfully hidden their traces beneath billions of years of geological change, leaving us to search for the faintest chemical whispers in a universe that seems determined to erase the evidence of its own history. Possibility because we now possess, for the first time, the analytical tools and theoretical frameworks necessary to conduct this search systematically and scientifically. The story of our investigation concludes not with answers, but with better questions and more sophisticated methods for pursuing them. Whether we are truly alone in Earth's long history or merely the latest in a series of technological experiments, the search itself has revealed that intelligence, consciousness, and the capacity for technological achievement represent remarkable emergent properties of matter organized in sufficiently complex ways. We have learned that the universe is both more mysterious and more knowable than we previously imagined, and that the greatest discoveries often emerge not from finding what we seek, but from developing the wisdom to ask questions we never knew we could pursue. The impossible question remains impossible to answer definitively, but in wrestling with it, we have gained something equally valuable: a deeper appreciation for the cosmic perspective that situates human technological civilization within the vast context of planetary and cosmic evolution. Whether we are Earth's first technological species or merely its most recent, we bear the responsibility of using our remarkable capabilities wisely, learning from whatever lessons the deep past might hold, and ensuring that our own chemical signatures in the geological record serve as monuments to wisdom rather than warnings about the consequences of intelligence run astray. The search continues, and the stones keep their secrets, but we are no longer the same species that began this investigation. We have become, in the truest sense, citizens of deep time.